I'm now recording you guys. So whatever you say, the other class is going to hear. Okay, so what colors are we feeling? Do we have a preference? Blue. Okay. Blue and pink. That's exactly what one of my other classes picked. Wow. Okay, so we're gonna start, and today we're gonna be doing some more stuff with those exponents like we did last class, but we're working with fractional exponents now. So we need to remember that when we multiply two like bases, we can add their exponents. Yes, we know that? Yes. So if I have something like this, then what would my base be? 6, right? And then I'd have 1/2 and I'd add 1/3, right? They're the same base, so I can add their exponents. But what do I need to do in order to really add those exponents? Common denominators, right? So what would be a common denominator here? 6. So how can I rewrite 1/2 as something over 6? 3/6. And how would I write 1/3? 2/6. So what's my exponent going to be? 5/6. Do we all understand that? Yes? So that would be my answer. Okay. I can also do it with a base that's just an x. So here, again, I'm going to add those exponents. So 2/3 plus 4/3. What is that going to give me? X to the what? Well, it'd be 6/3, right? Because we just add those numerators, right? Because we already have common denominators. And what is 6/3? 2. So this rule can actually help us to simplify those exponents so that instead of having to work with, 2/3 and 4/3, we can just work with something that's squared. Alrighty, can I go? Okay. So for the next one, we have the power of a power property. So that's saying when we raise a power to a power, we can multiply those two together. So like for this first one, we would say 4 to the 3/2, and we would multiply it by 2, right? So what happens when I do 3/2 times 2? But what's 6/2? 3, right? The divided by 2 and the multiplied by 2, those technically speaking cancel out. So we're going to get 4 to the 3rd. What is 4 to the 3rd? 64. It was just on your quiz, right? Okay. Similarly here, again, we can do it to variables. So we do 1/6 times 3. So we'd get what? Y to the what? Yeah, so it would be 3/6. And what is 3/6 reduced to? 1/2. And we do want to reduce it down as far as we can. So if you do need to multiply out and then reduce, that's totally fine. Can I go? Alrighty. Additionally, we can do the power of a product property. So that just basically means we can take this exponent and we can give it to each of those little pieces. So like in this first one, we can distribute this 1/2 to both the 9 and the 4. So we can say 9 to the 1/2 times 4 to the 1/2. How could I rewrite 9 as something to a power? 3 to the 3 squared. And how could I rewrite 4? 2 squared. And again, we just said, what would I do with those two powers there? Multiply them. So what's 2 times 1/2? 1. So do I need to include that one? No, so just be 3. And again, what's 2 times 1/2? 1. So it'd be 2 to the first, so that's just 2. And 3 times 2 is 6. So again, we can use this to kind of help simplify. You also could have multiplied 9 times 4 and simplified it that way. You would have gotten the same thing. But this works especially nicely in pieces like 6 where our exponents are a little bit different, right? So again, I can distribute this 2 out. So I'm going to get 8 to the 1/2 squared times 5 to the 1/3 squared. So what is 8 to the 1/2 squared? Eight to the 1/2 and then squared. What do I do with those exponents? I'd multiply them and they'd cancel. Do we understand that? So I'd just be left with 8. Okay? And then what happens to the second piece? It'd be 5 to the what? Two-thirds. Okay. And that's because 1/3 times, this is technically 2 over 1. Yes? Do we understand that? So that's how I'm getting the 2/3. Are the fractions what's tripping us up a little? Maybe? Okay. Can I go? Again, with a negative exponent, we can drop it into the denominator and make it positive. So this would be 1 over 25 to the positive 1/2. How could I rewrite 25? 5 squared. So we have 5 squared to the 1/2. So what's that going to become? Just 5. Are we starting to see that pattern of those canceling? So similarly, we would do 1 over 27 to the positive 2/3. That's the whole reason we moved it. How could I rewrite 27? What? 3 cubed. So 3 times 2/3, that's what we do for those exponents. What would that become? Multiplying. Okay. I'm multiplying 3 over 1 times 2 over 3, which is going to be 6 over 3. And what is 6 over 3 reduced to? 2. So it's 3 squared. And what is 3 squared? It's 9. Do we see how that can kind of help us simplify a little? We maybe just need to practice a little with our fractions. Maybe we'll do a booklet or something on that. Okay, can I go? Okay. And then when we have two exponents and we're dividing, we can subtract. So again, this one we would do the numerator exponent minus the denominator exponent. So what is 5/2 minus 1/2? Am I good to subtract those? Yes, right? Because they have the same denominator. Do we see that? So what would that be? Yeah, it'd be 4/2, which is going to reduce to 2. And what is 6 squared? 36. So again, 6 to the 5/2 and over 6 to the 1/2 looks really nasty. But then when we're allowed to simplify, we get to something nice, kind of like 36. So again, we can do the same thing with this. It'd be 2 to the 1/2 minus 1/4. Well, what do I need to do here? I need to get the same denominator. And what would be a common denominator? 4. So how could I rewrite 1/2 as something over 4? 2 over 4. So it'd be 2 over 4 minus 1 over 4. So this is 2 to the 1/4. Can I simplify that at all? Not really. So I just have to leave it like that. But hey, at least it's prettier than a gross fraction, right? And that can be your answer. We want to take it as far as we possibly can with the knowledge that we have. So 2, we can't rewrite it as something to a power, so we'd have to stop there. Alrighty. Again, we can also distribute that exponent out to both pieces. How do I want to phrase this? And we can also go the opposite direction. So if they both have that power, we can actually take it out of both. So looking at number 11, do you see how they're both raised to the 1/4? Okay, so one thing we're actually allowed to do is instead of just distributing that 3 out, I can rewrite this as 18 over 9, and I can take out that 1/4 from both of them. Okay. So I can, do you see how that's a power to a power? Yes. So I can multiply those exponents. So what would that exponent be? 3 over 4. Okay. And what is 18 over 9? 2. So this is 2 to the 3/4. Are we okay? We look perplexed. Yeah. Because this is a power to a power, so I can multiply those two together. So 1/4 times 3 is going to give me 3/4. Are we okay? Okay. So the reason I do this is, do you see how 18 and 9, they divide nicely by each other, right? So that's why taking a power out here benefits me. But in the next one, do these two divide nicely by each other? No, they don't. So this is where, okay, maybe distributing is a better option. So here is where I'm going to distribute to both pieces. So I'm going to give that 2 to the top exponent and 2 to the bottom one. And again, we're multiplying when we distribute that. So 9 to the 1/4 squared, I'm multiplying those two exponents. So what would that become? 2 over what? 4. And what is 2 over 4 reduced to? 1/2. And do we understand that's going to be the same exponent for the denominator? 25 to the 1/2. Okay, and how can I rewrite 9? 3 squared. And how can I rewrite 25? 5 squared. Again, do we see why our list is important? So squared to the 1/2, those are going to cancel. So then my answer is just going to be what? 3 over 5. A lot prettier to work with. Can I go? Okay. Again, does 16 over 81, does that really simplify? They do not. So we're going to go ahead and we can, again, give that exponent to both pieces. So that means 16 to the 1/4 over 81 to the 1/4. Okay, so now let's see if we can rewrite them. So how could I rewrite 16? I could write it as 4 squared. Yeah, so if I write it as 4 squared, is things going to cancel out totally the way I want it to? No, but I could also write 16 as what? 2 to the 4th, right? And that'll cancel out really nice and pretty. Do we see that? So there is more than one option there, but we want to go as low as we possibly can. And then 81, again, I could write that as 9 squared. Was that really going to help me? No, how else could I write it? 3 to the 4th. So 2 to the 4th to the 1/4, what's that going to become? Yep, just 2 and over 3. Alrighty. So we did this a little bit last class, but we're working with cube roots a little more today. So again, when I am multiplying two cube roots that are separated, I can actually combine them together and multiply them together. So I can say the cube root of 4 times 16. Does anybody know what 4 times 16 is? 64, you were right. And is 64 a perfect cube? It is. What is the cube root of 64? 4. Are we okay there? Okay. So then we have this next one. So similarly, we can do the same thing with dividing radicals. So we can combine this into one radical because does 162, is it nice and pretty? No. So, but does 162 divide by 2? Yeah. So let's go ahead and divide them first to get a smaller number. And then we'll worry about simplifying. So what is 162 divided by 2? 81. And is 81 a perfect fourth root? Yeah. What is it? Well, okay, so we can rewrite it if you want to, if it helps you to visualize it as 3 to the fourth, right? And then what happens to that fourth and that fourth root? They cancel. So what's my answer? Just 3. Okay. So again, we could do the same thing here, but first thing we want to check, could these two divide? Yep, they can, right? So we do 32 divided by 4. Because if they can't divide, then we are going to have to simplify them separately. But if they can, then we might as well get a smaller number before we go that far, right? So what is 32 divided by 4? 8. And is 8 a perfect cube? Yes, it is. What is it? This one's 2. Okay. Whew. This is my least favorite part, and I'm really sorry for what I'm about to do to you. I love you guys. Okay, so the properties of radical exponents and radicals can also be applied to expressions when involving variables. Because a variable can be negative, positive, or zero, sometimes absolute value is needed when simplifying a variable expression. Absolute value is not needed when all variables are assumed to be positive. Okay, so do you guys remember earlier, like last class, when I said we can take the odd root of a negative number, right? Yes?
Yeah.
Like I could take the cube root of a negative 125, but I can't take the square root of a negative 25, right? So that similar property applies here. So whenever we're taking, like whenever exponents and roots match and they're odd, okay? So whenever that index is odd, then it's going to maintain the sign, okay? So what I mean by that is like the seventh root of 2 to the 7th would be 2, but the seventh root of negative 2 to the 7th would be negative 2. Are we with me there? Stare at it for a minute. Odd roots maintain their signs, meaning if it's negative under the radical, it's going to be negative when you simplify it. If it's positive under the radical, it's going to be positive when you simplify it. Okay? Even roots are a little bit different because if I took this, right? If I took the fourth root of 5 to the 4th, we all understand that that's going to be positive, yes? Okay. But if I raised negative 5 to the 4th, would that be a positive or a negative number? Positive, right? Because it's an even power. So what we get out is going to end up being positive as well. Did we see that? Okay. So because of that, when we're simplifying with variables, so instead of like with numerical values, when we're simplifying with an x, we have to include absolute value bars when we take out an even power. Yeah, so the 5 on the outside would have absolute value bars, which is why it's positive. So what I'm saying is like, let's say I took the cube root of x cubed. What would that be? X, right? And if I took the cube root of negative x cubed, what would that be? Negative x, right? It's maintaining its sign. Okay. Now what if I took the square root of x squared? What would that be? That would be x, right? But what if I took the square root of negative x squared? It would be x, right? Because the negative times the negative is going to be positive, right? So we would essentially call that the absolute value of x. Okay? We only have to worry about it with even roots and with variables. Okay? And we'll do some examples of that. Can I go? You did not learn that last year, so that is new. Okay? Yeah, okay. All right, so here, one thing we can do is we can split this up, right? So we can split this up into the cube root of 125 times the cube root of x to the 6th. Okay? Is 125 a perfect cube? Yes. What is the cube root of 125? 5. Okay? And the way we simplify exponents is we take, do you guys remember this from last year? Exponent divided by index. Does that ring any bells? You heard that word. Okay. So we say, how many times is 6 divisible by 3? 2 times. Is there anything left over? No. So that means I can take out an x to the 2nd. Okay. Now we need to check. Was my index even? Index. No, it's a 3, right? Do we see that? So do I need to worry about absolute values? No. We only worry about it when it's even. Okay? When it's even. When this little number is even. Okay? Alrighty, can I go to the next one? So again, we are taking, this time we're taking a square root. We can split it into the square root of 9 times the square root of x squared. What is the square root of 9? 3. And what's the square root of x squared? X. But this time, is our index even? Yes. Okay, so what do I need to put around that x? Absolute value bars.
Is that technically 3 times the absolute value?
Yeah. Mm-hmm. It's not that bad. We're going to start by, again, splitting it up. So what would the 4th root of x to the 4th be? X. Do I need to include absolute value bars? Yes, because it's even, right? It's an even index. And does 81, is it a perfect 4th? Yeah, it's what? With 3 to the 4th under the radical, so it would just be 3. Okay, are we okay there? All right. So the other thing we need to remember, and this is that exponent over index thing, is how we can rewrite things. So this is like our general rule. So I am going to remind you of what the properties of this are. So, okay. So this little I out here, this thing is referring to the index, right? So that word I keep saying, that is the index. What is our default index? It's 2, right? A square root. Do we understand that? So our default index is 2. So what's this little thing? What's under the radical? What do we call that? A radicand. And then this piece, we call this our exponent. What is our default exponent? Default exponent is 1. And so we can rewrite something like this as the radicand raised to the exponent divided by the index, which is really what you've been doing all along. Whether you believe it or not, you have been, I promise. Alrighty. Could I go? Okay. So the next section is just asking us to rewrite. Did it ask us to simplify? No. So should I simplify? No, we're just rewriting. So what is the radicand here? What's our base of this exponent? 7. What's our exponent? Exponent is technically 1, right? Because our default exponent, when we don't have 1 written there, is 1. And what would our index be? 3. So this we could rewrite as 7 to the 1/3. Okay? That's it. So the next one we would rewrite as what? 11 to the 5/. 2, right? Because our default index is 2 here. Do we understand that? So the exponent, it doesn't matter if it's on the outside of that radical or underneath. It means the same thing either way. So this one we do have to be careful. What do I have to be careful of? The negative. So when I do this one, I'm going to put -9 in parentheses just to be careful. Okay? Because I don't know whether that negative is actually going out front or whether it's staying with it or whatever. So I just want to put parentheses around it. And what would that be raised to? 6/5. Very good. Okay. We can also go the other direction. So how would I rewrite this? Fourth root of 19. And do I need to include an exponent? No, why? Because it's 1, it's the default, so I don't need to include it. What about the next one? What would this one be? Cube root 9 to the 4th. And we can put that 4th underneath the radical. Another option, if you wanted to write it as the cube root of 9 to the 4th, either one of those is acceptable. They mean the same thing. Okay. What about the last one? 7th root. What do we need to be careful about here again? The negative. So I'm going to throw parentheses around that negative. And we can put it to the 3rd underneath the radical. Again, another option would be you could say the 7th root of -10 and that whole thing raised to the 3rd. Both of those mean the same thing. Okay. Alrighty. Can I go? Okay. So now we're going to simplify. This is not my favorite. It's going to be great, though. I believe in you guys. All right. Let's start by splitting it up a little bit. So 32, I'm going to simplify that. So what is the highest perfect 4th root that 32 is divisible by? 2 to the 4th, which is 16. And it's 16 times 2. Okay, and I am going to split it up even further. I'm going to have to take the 4th root of x to the 6th, and I'm going to have to take the 4th root of y to the 8th, and I'm going to have to take the 4th root of z to the 9th. Okay, so what's the 4th root of 16? 2. And then I'm going to keep a 4th root of 2. Just chill in there. Okay, I'm going to wait for us all to be together. Okay, now again, we're thinking exponent over index. Well, actually, I'm trying to... No, I'm going to write it differently. I lied. Okay, what is the highest... like something to the 4th that I can take out of x to the 6th? X to the what? Okay, do we understand that x to the 4th times x squared is the same as x to the 6th? Okay. Now is this next exponent, this y to the 8th, is that nicely divisible by 4? Yes. So do I need to fiddle with that? No. What's the highest number out of z to the 9th that's going to be divisible by 4? No, I think I'm making it too complicated. Okay. How many times is 6 divided nicely by 4? Yeah, no, you're right. Do we know division?
So like 1/3.
Okay. Nope, I'm going back to the other way. Okay. Do we understand that this is the same thing, right? Because we're adding exponents, yeah? Okay. We understand that this is fine. And we can rewrite this as z to the 8th times z. Do y'all understand that nicely? Okay. So if I'm again just keeping this thing chilling out front. So do we understand that this x to the 4th and this 4th root are going to cancel? Yes? Yeah. Okay, so what can I take out? X. And then what's still left over though? X squared. And this was an even root, so do I need to worry about absolute values? Yes, I do. Okay. So 8 and 4 are going to cancel. What's 8 divided by 4? 2. So this is y squared. And again, squared is positive, but I'm going to throw absolute value bars around it just to be careful. Okay, and then again, how many times is 8 going to divide by 4? 2. So this is going to be z squared with an absolute value. And then the 4th root of z is what's left over, right? Okay, so now all I'm going to do is I'm going to rearrange some stuff. So I'm going to keep that 2 that's out front. I'm going to take out the absolute value of x, the y squared, and the z squared. And then everything that's under that 4th root, I'm going to put under 1/4 root. So I'm going to say 2 x squared z. See, this is weird because 2 years ago I taught this and it was equally confusing. And then last year I taught it and everybody was like, oh, that's easy. And then this year it's again like this. So it's so weird. Oh, no, no, they were not. Anyway, okay. Can I go? Okay. So really what I'm doing is I'm dividing and thinking remainders. So like, do we understand that 6 divides nicely by 4 once? Yes? Once. And then with a remainder of what? 2, right? Yes? Okay. 8 divides nicely by 4 twice. Yes? Okay. And then 9 divides nicely by 4 twice with a remainder of 1. So that's really what I'm doing. Okay? So we're going to try it that way this time. So again, I need to look at 54. I want to think about, okay, what's the highest cube root I can take out of 54? Okay, let's think cube roots. 8's a cube.
27.
Yeah, it's going to be 27. 27 times 2. What's a cube root of 27? 3. And then underneath the radical, we'll have a 2 left over. Am I going to need to worry about absolute values on this one? No, because it's an odd root. So, how many times does 6 divide nicely by 3? Twice. Does it have any remainders? No, so that means I can take out an x squared. Do we see how this is working now? Okay. How many times does 9 divide nicely by 3? 3 times. Are there any remainders? No. So I can just write that as y to the 3rd. And then how many times does 4 divide nicely by 3? Once, with a remainder of 1. And so that would be our answer. Okay, can I go to the next one? Okay. So, do I need to worry about absolute value bars here?
Yes.
Yeah, I'm going to. So I'm just going to put absolute value bars over whatever I take out. So how many times is 7 divisible by 6? What? Once. With a remainder of 1. How many times is 10 divisible by 6? Once with a remainder of 4. How many times is 12 divisible by 6? Twice with a remainder? No. And then how many times is 19 divisible by 6? 3 times with a remainder of 1. Yeah. Well, I tried to do that in the beginning, and you guys, I was like, how many times does 6 divide by 4? And all of you stared at me like I was losing it. So I did try to do it the easier way first, but then you guys were like, huh? So we did it the complicated way, and then we made it a little bit easier.
This is much easier to do instead of doing whatever we do twice.
Yeah, well, it is what it is. Okay. So that next page is your homework, and I am going to pull up a little booklet, and we're going to do that real quick, okay?